What's up, gangsters? How about some 3D printing nonsense? And yeah, nonsense, maybe, I don't know. This segment, I actually filmed this like a month or so ago, and it was originally something that I intended to include as part of another, part of a longer episode. And then I did the editing and I was like, okay, number one, this is just way too long because this is like 30 minutes of nonsense. And it's just terrible. I hated it and I did not want to pollute anything else with it. I feel like that what I'm going to talk about in this episode is important stuff, but it's super boring, super down into the minutia, out into the weeds, whatever you want to say, about tolerancing dimensional stability and orientation. So if you really want to just nerd out on some of the nuances of 3D printing, then maybe this video will be useful for you. Otherwise, yeah, skip to the next one. Okay, so in the last episode of the 3D printing adventure, I was running some test parts using the epax hard black resin that gone fairly well. I printed out this thing here and talked a little bit about the pieces, how they printed out, the assembly, stuff like that. Also was printing this Amerilabs town part and starting to print some of my own parts, like this little 1/32 scale P40 Warhawk seat. So that all went fairly well. Had just a couple of failures where, there just wasn't, like in one case, one of the seats just wasn't even there, which was kind of weird. Anyway, but I also mentioned that I was getting ready to switch over to the Anycubic Craftsman Gray resin because as good as the epax hard black is, it seems to produce really, really high resolution. Sometimes it's a little too much, and you see things like like you can see the build layer lines on the side of this seat really well. You can see all of this detail on this Amerilabs town file really, really well. And sometimes that's exactly what you want, but sometimes you also need a little better surface finish. And the theory, at least with the Anycubic Gray, Craftsman Gray, is that it's supposed to provide a sort of a compromise between resolution and surface finish. And so I've started to run some of that. And so just as a direct comparison, this is a pair of seats that I ran and then shot a little bit of Mr. Surfacer 1500 on, so you can hopefully really see the level of detail there. It's really, really fantastic. You get really crisp resolution. Those little tiny inset rivets, I believe, if I recall correctly, are 0.15 millimeters in diameter and 0.15 deep. And that's really getting down to what's possible to fully resolve. The thing is, on pretty much every form of 3D printing, inside dimensions are always going to be a tiny bit small, outside dimensions are always going to be a tiny bit large. And that's basically an effect called bloom. And what that means is, let's say that if you're using a masking SLA type machine like this one is, and you are masking such that this line right here represents the edge of your part. And so you've got pixels that are white here and here and here and here and here. And all of them on the other side of the line are going to be black. So you get UV exposure over here, but not over here. And so what happens is, like, let's say you're running anti-aliasing, for example, some of these pixels that are right next to where the line is supposed to be are going to be gray. But like, let's say this pixel right here is supposed to be white. So you're going to get UV exposure on that pixel, but the light scatters as it travels through the material. And so you get a little bit of extra outside the boundaries of this square that gets a little bit of curing. So it in effect makes the square a little fuzzy around the edges, a little larger, and so you're going to have some spillover over here on this side of the line where you get a little bit of curing. That's what makes an outside, or really every section, a little larger in that direction. So if this line represents the outside edge of a block, like the dimension from this side to this side, it's going to be a little big. If it represents the dimension from the inside to the inside, it's going to be a little small. That's just a fact of life with 3D printing, and you have to account for that when you're engineering your parts if they're going to be, if they're going to be mating pieces that fit together. Anyway, that's why when you get down to like 0.15 millimeters, your holes are going to tend to want to just fill in and not be visible anymore. So that's kind of why that's the lower limit. But here's the important thing is you can also kind of see on the side here that the build layer lines are not quite as offensive. If you look at both of them, it's kind of hard to get them sort of side by side with the angle the same. Let me get that one where you can see those, and then I'll try and match. Come on. Okay, surely we can see these. I can see them with my eyeball, but the camera sees it differently. Come on. There we go. Okay, now the fact that it's a little harder to get them to show up on the gray, on the anycubic gray part is, why there's, like I say, there's just a slightly bit softer. Anyway, that's maybe not even the best example. Let's do a direct comparison between this part here in anycube, or the epax hard black, and this one done in Craftsman, and they're both run at 30 microns, 0.03 millimeters. So you can, oops, I need to show you the same side if I want it to be a direct comparison, right? Anyway, so you can see with that one how crisp the text is, the Amerilabs logo, and look at the pie-shaped thing there. You can see like 5 or 6 slices of the pie. Now when you look at this one, you can see it's not quite as crisp. You don't get to see the slices of the pie quite as well. So, and that's what you see with this Craftsman resin, is that for little tiny features that are on any face that's especially close to horizontal, you get really pretty good resolution. But these vertical faces, you get a little bit more minimization of build layer lines and things like that. So anyway, I think it's a pretty good comparison. Again, this part is run in the at 0.03. Actually, this one I think was run, this black one was run at 0.05, but this one definitely run at 0.3. And you can compare on curved surfaces. You can see how much the layer lines show up there on that, and then that's, they're quite a bit less noticeable at 0.03. People talk about, diminishing returns, and you'll hear a lot of people say, oh, there's no point in printing any finer than 0.05. If you're doing stuff like figures, yeah, that's probably true. Not a lot of point in it. But for mechanical parts, you definitely will see some differences. Like here is an example. This part right here, okay, this I ran last night. This is in the Anycubic Craftsman, and it was run at 0.02. And look at how nice those curved upward-facing surfaces are. You can just, the build layer lines are just really minimized. And look at the little round protrusions, cylindrical protrusions on top of that building in the back. There's only 4 or 5 of them, I think, missing really, really good resolution. And then when you flip it over and look at the features back here on the back, you can see how crisp and nice those numbers are. It's just really, really good. So I kind of feel like that for mechanical detail parts in Craftsman Gray, that what I'm going to be trying to run is 0.02 at layer thickness. I think that'll work pretty good. Now, here's another sort of comparison that I wanted to show you guys. There's a lot of parts here. You can see these landing gear parts and wheels. These are an interesting case study. This set of wheels and the landing gear right here were run at 0.01, so 10 microns, and stood up vertically. This is another one of the landing gear. You can see how I built it. You can see where the supports are. They are all on bottom facing surfaces that you don't see much when the model is sitting in its natural orientation. The other thing is that this cylindrical feature here of the main gear leg is pretty round. I've measured it and it's pretty close. And I got really nice definition in that hydraulic damper cylinder on the front there with those grooves on it. You can see that better right here. Let me pull this out. This is all for test fitting on a project. So this is pretty good. You can see the resolution is really nice. But, so this is kind of getting into talking about orientation. Because again, we've always got people saying, like I saw a guy in SMCG day before yesterday said, you should be building everything between 40 and 46 degrees depending on your machine. I was like, okay, yeah, horse shit. And here's why, okay, just in case I have not managed to make this clear before. So here's a couple of other orientations of the landing gear, okay? So, what are the penalties of running this one vertically? Well, it's taller, obviously, and especially at 0.01 millimeters, it takes a while. But, you know, the advantages are, again, the supports are on the bottom. I get good cylindrical accuracy. Now, where I did not get good cylindrical accuracy, maybe you'll be able to see it, is on this axle shaft sticking out of that flat face right there, okay? See that axle shaft? You can see it's, you know, where the wheels attach, okay? So if you look at that, you can see that it is definitely not round. It's very flat on the bottom, so not good cylindrical accuracy, and it has a bit of an upward tilt. Now, I probably should have put a support on the tip of that, but I wanted to see how it would do. Point being is, it's always a compromise. Okay, so I've got really good cylindrical accuracy in the Z direction by building it this way, but then I've got these other cylinders that are orthogonal, and so they don't come out as good. So you think, all right, well, let's tilt it over. Let's see what happens there. All right, well, if you go all the way and decide that the little axles are the most important cylindrical feature and you want ultimate accuracy on the diameter of that axle, well, there you go. I can lay it all the way over on its side and I can get nice axles. But look, I've got build layer lines on those angled surfaces of the strut, and they're going to show. So they're going to have to be dealt with. You've also got build layer lines now on the sides of the part. Hopefully you guys will be able to see this. I'm trying to get the light as close as possible. You've got build layer lines that show up on the sides of the part. They're not as big of a deal, but it's not nearly as good in terms of surface finish as this one is on the vertical surfaces of the strut. But you do still have some of the pixel definition there on the sides of the cylinders. All right, but obviously now you've got supports all along one side of this landing gear, and when you remove those, no matter how carefully you do it, you're going to create some defects. Those are going to be problems. There's also some issues along the bottom faces of like the scissor link there, where it's not quite so good. So what about a compromise? All right, well, this one's tilted over at something. I don't remember exactly, but it looks like it's about 30 degrees. Just lining it up with that line on my workbench, that line's at 30 degrees. So, okay, so that's tilted over 60 degrees from vertical. You can see, again, I've got supports on all those faces to deal with. I've got build layer lines, which again may or may not matter. Got pretty good cylindrical accuracy on all of the features, so that's not too bad. You'd think in terms of accuracy that's pretty good, but again, I've got to deal with some support attachment points, but they're not nearly as offensive as they are if it's laid clear over flat. They are relatively easy to get to, and I might be able to do some experimenting and figure out how to minimize those. But you can see this bottom surface here, bottom edge there of that section right there, not very square and crisp. Doesn't really show that much when the thing is assembled, so might not be as big of a penalty. But I definitely have a bunch of build layer lines on those scissor links right there that are certainly going to show. So point being is there's always trade-offs to be made. There is no single perfect orientation for any mechanical part. It seems really obvious to me, but I think a lot of people just seem to have a hard time grasping the reasons why. And hopefully this gives you some direct evidence as to why that's the case. Going to these wheels, okay, so I printed the first batch just standing straight up. And the treads, and these are printed at 0.01, the treads came out pretty good, really nicely defined. And my supports were minimal, just on the very bottom there, so that's really nice. You can see that there's almost no build artifacts, just a little bit on the sides of the tire, okay? Not too big of a deal, but the big hex nut right in the middle there is sort of flattened on the bottom. Did not start out printing very well, so maybe I needed to put a little tiny support there, but again, I risk screwing up the appearance of the geometry. And if you look at the axle hole, you can see that it is very definitely oval, and in fact I only had a 0.2 millimeter clearance between the hole and the axle stub, and it wouldn't go on. I had to drill it out. So there you go. Penalty there. So I went back and I ran some more wheels at different orientations, laid this one down almost completely flat. It's like just a few degrees from flat. And the reason I couldn't lay it perfectly flat was because the rim of the bead right there, where it meets the rubber on the bottom side, was going to be a ring-shaped island, which I obviously could not have. So I had to tilt it just a little bit, and you can see I got a shit ton of little supports under there. But it doesn't really matter, because look inside the rim. You can see, hopefully, you can see all of the build layer lines inside the rim. I can see them really well from where I'm looking at this, but I'm not sure if they're going to show up on camera. Maybe. They're 100% in there. If I could just get the shadow correct. Anyway, you can also see a lot of build layer lines on the surface of the tire carcass. You can really see those right there. It's just not good. I mean, for me, that's just not acceptable. I mean, it's fine at normal, like eyeball viewing distance. It's good. I can barely see them. But if you're taking a close-up photograph, it's going to be obvious. And if you do any sort of dry brushing or anything like that, that texture is going to instantly start to pop out. So again, I thought, all right, well, let's compare to building them on their straight up. And so again, these are built at 0.02. Again, you can see the bottom of that big hex nut feature, not good. Should have put a support there. The hole, again, you can very clearly see that the hole, which I've enlarged a little bit, not round, and the hub is no longer cylindrical. So that's not good. So what about this angle? This one is exactly 45, which I just chose arbitrarily. And this one is the best in all respects. You can see really minimal build artifacts. What looks kind of like might be some build artifacts on this one where I accidentally touched the primer while it was still wet. There's a defect in there. I don't know why I got that horizontal line across that left one. That's a defect. I'd have to reprint that. But in terms of orientation, this is absolutely the best compromise for those parts. Little bit of artifacting on the top and the bottom. But I have not checked the dimensions here. We could go ahead and just take one of these off. Really should clip it off, but it's not a big deal. Again, 0.2 millimeter support attachment points are very nice. You can see how easily that comes off, and the scarring is very minimal. So let's look at that hole right there. So pretty good, pretty close to round. Not bad at all in terms of its cylindricity. Let's see how it fits on one of these axle stubs. And I gave it, now it's got a 0.4 millimeter clearance. And that's a lot, goes right on. In fact, it's just too loose. Like, I wouldn't want that much clearance, really. These are going to be resin cast probably, so I might leave it that way. But yeah, so obviously it goes right on there like that, no big deal. So anyway, there you go again, just kind of a study in positioning, orientation, tolerances, that sort of thing. Now let me talk about one last thing here with regard to also positioning on the build plate, because you get people who will say, don't ever build anything flat on the build plate. Well, that's absurd. Again, there's times when it absolutely makes the most sense. Like, for example, I've got this little box. This is the wheel well part for this landing gear, and there's really not any reason to put it on a raft or put it on supports or whatever if I don't have to. So I just built this straight on the plate, and it did fine once I dialed my settings in. I had some problems getting it to stick. This was run at 0.01 and looks great, except for, yeah, that obviously is not right. And that's connected to what happened here, and I'll explain this directly as well, because these flat plates with these little nubs sticking out of them were part of a sort of a challenge that I set up for myself, and I'll explain that here in a minute. But here's the thing. So whenever you print parts, there's obviously a certain amount of it that has to be stuck to the build plate. I mean, the bottom of it always has to be stuck to the build plate. But you've got this constant tug of war between the build plate and the FEP, or the INFEP in the case of the epax machine, which is supposed to have a lower stiction, and that's what you want. Okay, so basically you've got suction force that creates that tug of war. So what happens is that as you print a layer and the build plate raises up, you've got, I mean, it's a solid piece of material between the build plate and the previously printed, it's a solid connection, if you will, between the previously printed layer and the FEP, right? And so like, let's say that you've printed and you're all the way up to this very top layer, okay? This surface is trying to stick to the FEP. This surface is trying to stay stuck to the build plate. And if this doesn't stay stuck, then the part can shift around or get pulled completely off and you have a failed print. And that's why you have burn-in layers. Like the default for this black resin from epax is that you have 4 burn-in layers and you run those at 25 seconds exposure, as opposed to a normal build layer, which is only going to be run at about 2 or 3 seconds exposure. And the whole idea is that you cook the resin enough that it just basically gets glued completely to the aluminum surface of the build plate, and that stiction is more than the stiction between this face and the FEP, and so the build plate ideally always wins the tug-of-war, right? Well, so that obviously failed to happen here. I improved things on this one by adding a little bit more of a burn-in time on those initial layers, and that made this part stick a little bit better. And that's also what I had to do here with this challenge. So what this was supposed to be, this was my buddy Matt McDougall. He was trying to print a whole plate full of little bitty flange bolts with about a 0.9 millimeter head and a 1/2 millimeter shaft. And he wanted to do this whole raft of them, and he was having trouble with it, wasn't sticking to the plate, etc. So I'm like, hey, I want to try that. So I did, I tried it, and it was an instant fail. And you can see what happened here is that this surface, which was supposed to be stuck to the build plate, and you can see where it did because it's got the bead blasted texture imprinted in it. And then these areas here that clearly were just getting pulled up because there was so much stiction against the FEP. And so what happens is the part gets stretched vertically. Like that's only supposed to be 3 millimeters thick. It's obviously significantly more than that. Not only did it get stretched vertically and made taller, but it gets shifted over because the FEP is flexible and elastic up to a certain point. So you get the thing shifting around, and this part was in that same build, and so it also suffered a similar penalty. Same thing with this thing here. It obviously got screwed up as well, and you can see the bottom of it shifted all over the place, just did not stick. And so what happens then is as those large flat layers get pulled further and further up in the Z direction, they basically bury all of those little bolts, which are supposed to be sticking up about 0.2 millimeters. Or not 0.2, but 2 millimeters. The little shaft is 2 millimeters long. So yeah, total fail. The heads on some of them are not too bad, but still, that's not going to help. So I thought, well, this is basically a mathematical equation. What you have is a certain amount of force in pounds per square inch that's required to separate the printed face from the FEP versus the amount of force that's required to pull it off of the build plate. And obviously, the more surface area you have, the greater the amount of force, and so there you go. I mean, this is it's just basic physics. So I thought, well, what if I just make this a third as big, and then I'll have much less force pulling. So that's what I did. You can see about a third as large. Yeah, that's my cat. She's telling you that this was not a great idea, still didn't work. Yes, thank you for the help. Anyway, as you can see, I have the same effect on the first try. I got separation between the burn-in layers and the regular layers. Did not stick, and it's a fail. So I thought, all right, well, again, what could I do to reduce the surface area and create a little less suction? So I did this. I perforated it with all these holes. Well, yeah, that wasn't a terrible idea, except that then what happened is, as the build plate is moving up after each layer is printed, it's creating a vacuum that's trying to suck uncured resin upwards through these little holes, and that has to come from someplace, which ends up being from the sides of the part. And you can see how these little channels opened up underneath, and it was actually pulling resin through those and making the stiction even less and less on the build plate. And this obviously was a fail. Closer than this one, but still a fail, because those are supposed to be, I think maybe those are now, I shortened them to 1.5 millimeters, so most of them I got, not bad. You know, maybe it's enough for whatever you have to do. I think Matt only actually needed like 10 of them. Anyway, so then I thought, all right, well, let's do this. Let's make the raft where it's just, there's no way it can trap any resin. It's got the minimum amount of surface area, and everything, at least in theory, should now be solved. So I created a 0.5 millimeter thick raft at the bottom, and you can see that I've kind of built this thing like a pallet, and it's got minimal actual surface area. It almost worked, but you can see still lost stiction on a big part of the bottom of it, and it, suffered some warpage. Now, by the time it actually got to the point of building the little bolts, they were fine, and so all of the bolts are perfectly successful. I lengthened them back to 2 millimeters long, and they all printed wonderfully, and you can see the crisp definition at the of the heads. Maybe if I can get them in the right light here. Anyway, yeah, pretty good. Really, really pretty nice. Anyway, and another thing I should point out is that I was trying to do these at 0.1 or 0.01 millimeters, so 10 microns. 10 microns did not work. This one I went to 20 microns, and it was better. This one I also did at 20 microns. Okay, there you go. I told you, you were warned, but if you suffered through all that, I hope you found it valuable and that, all that made sense. Obviously orientation is a thing, dimensions are a thing, tolerancing is a thing, but only under certain circumstances. If you're printing figures or busts, none of this stuff really matters, because you just about can't screw those up in any of those three areas. Yeah, if you print your bust standing on its head, then maybe that's not going to be the best. But otherwise, it's kind of hard to screw it up. This really applies to when you are engineering scale model parts that have to fit together or fit with something else and have, like an A surface and a B surface in terms of appearances. So anyway, yeah, I'm going to stop rambling, shut my mouth. This is long enough already. But as always, I appreciate you watching. Much love.